Il prossimo intervento è da parte di un collega e un amico, Ignacio Martinez-Moyano, di Argonne National Laboratory. E Ignacio è anche un membro della System Dynamics Society, oggi è qui intanto come esperto del progetto ATTACS e in più il CIS Sapienza, coordinatore del progetto ATTACS, ha in piedi un accordo quadro con Argonne che riguarda anche la possibilità di collaborare ovviamente su progetti di ricerca in generale, scambio di ricercatori eccetera. Ecco, grazie Ignacio, please.
But it's embedded in the presentations.
I hope it works,
yeah,
because actually there have been a few issues with codecs and stuff like that. Anyway. That's it. Hopefully. Don't blame on me if it doesn't.
No,
please.
I know.
All right, so we'll put it into presentation mode. All right. So since we need to try to stay within the lunchtime.
Hello. My name is Ignacio Martinez-Moyano. I'm with the Argonne National Laboratory in the United States. And also I have a joint appointment with the University of Chicago. And I'm very happy to be here. I hope that what I can share with you it's useful. And I'm going to try to go relatively fast, but not talking too fast. That's what I've been told, so that they can translate. Hopefully that'll be the case. I'm going to be chatting about some of the work that we do at Argonne. I don't think I'm going to have the ability to say everything about every single one of the models. And actually, I'm just going to talk about 3 different models that we thought were really relevant to the contents of this specific conference. And I think that these 3 are more aligned, although these are not the only ones. We have a very, very big portfolio of projects that we are pursuing. And first, I'm going to just let you know that the general outline then is these 3 projects. And also, I'm going to talk a little bit about the origins of what we do at Argonne, and then some final thoughts of what we normally try to accomplish with these modeling projects. The Argonne National Laboratory is part of a network of DOE national laboratories. DOE stands for the Department of Energy in the United States. So we are managed, as you can see, all of those dots represent the different laboratories. We have 17 of them. Argonne, of course, is the best. Of course. But definitely not the largest. It is relatively small compared to others. We have 4,500 people working there, out of which 1,500 PhDs doing research. So it's not the biggest, not the smallest either. But it's the oldest for sure. It's the very first one that was put together. Actually, it's a spin-off of the Manhattan Project. So originally, the Manhattan Project took place at the University of Chicago. And Enrico Fermi was working there and produced the science for the atomic bomb. And then the actual engineering happened at Los Alamos National Laboratory, which is where the testing and the engineering happened. But the difficult and tough part was performed by Enrico Fermi, of course. And that was what eventually became Argonne National Laboratory. So we are in Chicago, and we are managed by the University of Chicago for the Department of Energy. Other labs are managed by other universities and some other organizations. Some other universities that actually manage laboratories are MIT, Berkeley, UC Berkeley, and others, Stanford, I think. So part of what we do is to try to engage with the government agencies and actually private organizations to tackle projects that we consider that are really important for the national interest. So we are not involved in relatively simple things. We try to get involved in really complex things that would require a lot of expertise of different areas. The first one of those projects that I would like to talk about, and by the way, I think that it's perfectly okay because I have just a few remarks to say about these projects. If you have any questions, please go ahead and interrupt me. It's perfectly okay, if that's okay with the organizers, of course. But I'm perfectly okay with that. So the very first project that I would like to share with you is it's one project that we've been involved in for the last few years. And this has been funded by the Department of Homeland Security and the Department of Energy, in which we are modeling subways. We've been modeling that for quite a few years. And basically, we call these the tools for underground transit systems. One of the things that we do is to try to understand what is going on at the very, very detailed level so that we can actually use this for designing interventions and for helping emergency responders to actually be able to accomplish things on the ground. So this is something that has been going on for quite a bit. And one of the things that we do is create these detailed models that include components that are system dynamics in the approach and also agent-based in the approach. And additionally, we have a number of experts that are explosives experts and also physicists that help us actually understand how these actually behave, how the propagation of certain agents behave at the very molecular level, then we can actually introduce that into our models. So we have subway models of gas and particles, how those are transported in case of a release. We have also models of the passengers, and these models are behavioral and social models of how passengers do things within the system and how they would react in the event of an emergency. And also subway to outdoor and outdoor to subway mechanisms. And the very last one is subway to facility and then facility to subway. So all of these, although these seem quite complex, it's at a certain level really simple. We're trying to map the different characteristics of the subway stations so that then we can actually theoretically and in a simulated world release toxic agents and see what happens. Some of the actual subway systems that we have modeled and we study are listed here. So New York City, Washington, Chicago, and all of these are actually modeled at the very specific level of the stations and subway trains and the vents, everything that includes each one of these systems in very, very real detail. So we have a number of organizations that we need to interact with, including, of course, the local first responders, the authorities, the city itself, and also the police and everyone involved in the case of some emergency happening. We have, of course, the actual models that we produce are, in some cases, depending on what type of thing we're doing, are restricted and classified because of the vulnerabilities identified, and we don't want that to go outside of a constraint mechanism. But one of the important things, I think, is that these models, by the way, I think I'm chatting, I'm talking too fast, sorry. But these models are designed so that we can actually intervene. Once again, we do things in such a way that then first responders can actually take the results of these models and actually change the way they do things in the real system. I'm going to try, I hope, to get this to work. This is supposed to be a simulation. Can we try? No, this is the animation, actually. Yeah. Oh, it's right here. So what you're seeing is an animation of an actual model. As you can see on the left, You see a clock going for a 30-minute simulation of what was going on. I'm going to get it started again. The different colors represent the different concentrations of the toxic agent that has been released. And the subway system that it's there is actually is not real. It's a fake one that we produced for this presentation. But I'm going to do it again. But one of the things that it's interesting is how the concentrations vary depending on the different cars of the subway going, through the system and carrying part of those particles with it. And what you see outside is a plume of the release once it goes outside of the system through the vents. And actually, the model that we have to create the plume, it's a buildings aware model. So this specific model actually takes into account all the buildings that are in that specific area of the city, the shape, the topography, everything, where are they sitting, what type of materials they are made of, and actually how that actually changes the way in which the plume of the toxic agent progresses over time. Of course, you might say, well, it is going to be way different if it is on a sunny day than on a rainy day, than if it is going, the wind going west or east. And you're completely right. So we conduct thousands and thousands of simulations to try to figure out what types of problems these could happen. So here is once again. So it starts in the middle of the system, and then it starts to propagate. And in some cases, as you see through the system, some of the cars stop, some of the actual cars are not taking any material with them. It just flows through the system in a half hour. And also we have models of how the agent actually attaches to individuals in their clothing and in their persons, and how that actually changes their behavior depending on if that is being, creating some sort of problem in their motor abilities or things like that. So we have, as a result of this, a number of casualties that are forecasted and things like that. So these are the types of models, really detailed models, in the sense of we have all the people being simulated, all the trains, all the stations, all the buildings, everything there, so that we can actually push a certain scenario out, and specifically with the meteorological conditions that we would expect at a certain point, and see what happens. And once we have all the results, we provide those results to the city and to the first responders and to the police, and they would figure out what to do with it. These models are actually validated by experimental conditions. So most recently, a couple of weeks ago, we had an experiment conducted in the real system, in the real subway system in New York City. So we announced it way in advance, and then we released actual, simulated toxins. Of course, we're not going to release a true toxin, but things that are kind of like the same in terms of their propagation and their mechanisms and the molecular activity and how they attach to the people and everything. So we did do that with the cooperation, of course, the New York City officers and police. And we conducted all that so that we could actually validate the results of this model with experimental conditions. And we've done this in several areas in the US. So that is the first part. The second model that I want to talk about is how we approach resiliency. We've been modeling resiliency for a few years now, starting in 2014, as part of an idea that we said, well, we've been doing a lot of emergency preparedness, and also we want to understand how these systems can go back to where they were before the either man-made problem was generated or a natural disaster happened. So a Center for Integrated Resiliency Analysis was set up, and one of the things that we by now understand better is that we want to focus these type of studies of resiliency on the characteristics of the community and the systems that actually contribute to that. And I think that that's important in this forum, because one of the things that we consider at the core is critical infrastructure, of course, as you might imagine. But not only the critical infrastructure in the traditional sense, we had been simulating and modeling that for many, many years. Now we do it as part of an integrated mechanism that allows us to see the bigger picture, not only the infrastructure, but also that all the social systems that actually interact with it. We call that the ARISE approach, the analysis of resiliency for integrated system effectiveness. That ARISE approach allows us to see how the resiliency at the community level, or we want to understand that as resilient communities, actually are able to create those mechanisms based on, as you see here, the different critical infrastructures that actually interact with them. But most importantly, as you see in the bottom, what we call the human landscape. So we want to understand how humans interact with the critical infrastructure and how humans actually, through their mechanisms of trust in government and confidence in government, are able to either help the emergency responders and help the communities to go back up to where they were before, or actually hinder those mechanisms. So if trust is high, then things are going to happen in a certain way. If trust in the government is low, things are happening in a very different way. This ARISE framework actually allows us to see this problem as a 5-pillar mechanism in which, as I was saying, part of what it's really important for this audience is what we call the enhanced societal capacity. But that is one of the pillars, thinking about how to enhance this societal capacity, and that is through the processes of understanding the infrastructures, and particularly we are very focused on the public health system, but also on how all the infrastructures actually create enough capacity within society to then bounce back. But it is one of 5 mechanisms that we think are critical in this respect. We've conducted a number of studies about how to actually assess these mechanisms, and that thing that looks like an Excel worksheet, that's precisely what it is, an Excel worksheet. And we use that as mechanism to actually capture information about the resiliency of the community and help communities understand where they are sitting in terms of a series of indicators. In this case, we have hundreds of indicators that then are aggregated up, and we are able to provide a view, a systemic view of where resiliency sits. And this has helped local and state governments to figure out what areas they should improve and change. Also, we are moving more into the dynamics of how these drivers change over time. So as you can see here, at the very center, there is a box that it's called community resilience. And this is using the system dynamics approach. So those boxes represent accumulations, and the double arrows in and out represent inflows and outflows to those accumulations. Basically, things that build them up or actually erode them over time. And here, this is a very notional representation of a model that we have, in which we build community resilience as a function of things happening in all infrastructures within that community. And depending on the level of infrastructure and how you are able to actually generate enough capacity there, that changes the level of the community resilience. Then last one of the models that I would like to chat about is one very interesting effort that is led by my boss, actually, Charles Makel. And he's been very much engaged in modeling Chicago. We have now a sitting infrastructure based on agent-based modeling and system dynamics modeling, in which we have 2.9 million individuals individually modeled there, and also 1.2 million places, according to that description, which generates interactions between people and infrastructure at a very specific set of geographical locations that yield close to 3 trillion exchanges over time. So we model this in a temporal resolution of 1 hour, And that creates a very realistic mechanism in which we have these virtual individuals, but are very much related to the actual individuals in Chicago. We actually derive that from census data. Although synthetic population, we actually use it with synthetic data that it's inspired and statistically indistinguishable from the true data from the Chicago individuals. They interact with the infrastructure, they interact with everything that has to do with the social fabric of Chicago, and we're investigating problems such as disease transmission, violence, erosion of certain aspects of what constitutes a good city, etc. This is one interesting model that has been under development for a couple of years now. And finally, what is it that we are trying to accomplish with these models? Well, it's really simple in the sense that we want models that are used and that are actually useful. And what type of things we want to get out of them so that people can actually use them for. We want them to be, the people that use them to be able to derive what we call dynamic thinking and insights, that they actually see things over time. We want them to be able to derive structural thinking, that they can actually see by the structure of what is going on, derive interesting mechanisms that they could actually influence. Also, they should derive operational thinking. They can actually see things happening the way in which the real system behaves. And we want this to be generative, so that generalize.
Now the final conference of the ATTACS project. Ah, scusate, io vedi, vi ho appena detto che avremmo fatto la conferenza in italiano e sono partito diretto in inglese. Vabbè, è un classico. La forza dell'abitudine, adesso poi me la tiro perché sì, lui parla in inglese. No, ma vi assicuro che certe volte si perde completamente diciamo la differenza in certi contesti. Benvenuti. Grazie della vostra presenza. Oggi concludiamo, diciamo, formalmente il progetto ATTACS, finanziato sul bando 2013 del SIPS della DG Home. E adesso poi vi daremo tutti i dettagli, insomma, comunque stiamo qui introducendo per ora la questione. Volevo darvi intanto alcune informazioni di servizio rispetto al programma che avete nella brochure. Non ci sarà l'intervento della dottoressa Calipari, che ha avuto diciamo un problema diciamo di governo, quindi che anche prima del discorso breve.
That they actually take the simple model and take it to the big problem and be able to use it. And at the very end, we build these things for scientific thinking. We don't want them to be just representations of what is going on, but actually use it to test hypotheses and theories about what could happen and how to actually change it. Thank you very much.
Thank you very much. That was, mi sembra che sia stata una brillante presentazione di ciò che si può fare, no? con questi strumenti. Una parte, diciamo, di quello che avete visto è un po' anche alla base del progetto ATTACS, quindi ci sembrava che l'introduzione da parte di soggetti che anche si occupano di questo tipo di approccio e di questo tipo di progetti fosse un buon modo per introdurre i concept che stanno alla base del progetto ATTACS. Ora lascerei, ecco, mi sembrava molto importante l'aspetto, tra l'altro detto da Ignacio, mi sono appuntato, sul fatto che anche il progetto ATTACS prevede così diciamo, lo studio di queste situazioni, e di certo non si propone di dare oggi delle risposte precise. Questo lo riprenderò poi quando faremo la nostra presentazione. Quindi è vero che dà delle risposte in termini qualitativi e anche numerici su un certo tipo di comportamenti dei sistemi sotto attacco e in generale che stiamo analizzando, ma insomma, visto che poi progetti di questo genere molto spesso richiedono milioni e milioni di euro e tempistiche che vanno ben al di là anche di un buon Horizon 2020, direi che chiaramente l'analisi e lo studio per capire cosa potrebbe succedere e quelle che sono le dinamiche dei sistemi e quindi a cosa attraverso queste dinamiche si possa arrivare sono chiaramente particolarmente importanti.